Enceladus is hiding something, and it's not being subtle about it. This moon, barely 500 kilometers across, a frozen snowball orbiting Saturn, is shooting columns of water into space. Not occasionally, not gently. Geysers of liquid water erupting through cracks in the ice at roughly 1,300 kilometers per hour, blasting material so high that it escapes the moon's gravity entirely and feeds one of Saturn's rings. A world that small should be cold, dead, and geologically silent. Enceladus is none of those things. And what we found inside it is the kind of discovery that keeps astrobiologists awake at 3 in the morning, staring at data they're not sure how to interpret. For most of its known history, nobody paid much attention to Enceladus. William Herschel spotted it in 1789, a tiny point of light near Saturn, and for the next 2 centuries, it remained exactly that, a dot, one of dozens of moons in Saturn's system, unremarkable compared to the giant Titan with its thick orange atmosphere and methane lakes. Textbooks gave Enceladus maybe a paragraph. Small icy satellite, high albedo, diameter 504 kilometers. That was the entire entry. If you told a planetary scientist in 1995 that this particular moon would become the most important target in the search for extraterrestrial life, they'd have thought you were confused. They'd have pointed you toward Europa or Mars. Then Cassini arrived. The Cassini spacecraft entered orbit around Saturn in July 2004 after a 7-year journey from Earth. Its primary targets were Saturn's rings and Titan. Enceladus was on the observation list, but it wasn't the headliner. Nobody builds a nearly $4 billion mission to visit a 500-kilometer snowball. That calculus changed during the first close flyby in February 2005. Cassini's magnetometer detected something that didn't fit. The magnetic field around Enceladus was distorted, bent in a pattern that suggested the moon was actively pumping charged particles into the space around it. A dead, frozen world doesn't do that. The science team at JPL scrambled to adjust the mission plan. They redirected the spacecraft for additional close passes and pointed every instrument they had at the South Pole. What they saw stopped the conversation cold. Enormous plumes of water vapor and ice particles were erupting from 4 parallel fractures in the South Polar ice. The fractures were warm, far warmer than the surrounding terrain, radiating heat that had no business being there. Each fracture stretched roughly 130 kilometers across the surface, like claw marks raked through the ice by something massive. Scientists started calling them the Tiger Stripes, Baghdad Sulcus, Damascus Sulcus, Cairo Sulcus, Alexandria Sulcus. Each one a vent, and each vent spraying material into space with enough force to reach altitudes of hundreds of kilometers above the surface. Some of that material fell back as fine snow, coating the terrain around the vents in fresh ice crystals. The rest drifted outward, escaped the moon entirely, and became part of Saturn's E-ring, the faint, diffuse ring that wraps around the planet. At Enceladus's orbital distance, this tiny moon was building a planetary ring in real time. Saturn's most ethereal feature, the E-ring, wasn't some ancient leftover from the planet's formation. It was being manufactured right now by geysers on a world smaller than the state of Texas. So where was the energy coming from? A world that small has almost no business being geologically active. The surface temperature on Enceladus averages around -201 degrees Celsius. It receives almost no solar energy, orbiting roughly 1.4 billion kilometers from the Sun. Its mass is far too small to retain significant internal heat from its formation. By every reasonable thermal model, Enceladus should have frozen solid billions of years ago. It should be a dead ice ball, cratered and inert, indistinguishable from 100 other minor moons in the outer solar system. The answer, or at least the leading theory, involves Saturn itself. Enceladus orbits Saturn in a slight ellipse. nudged into that elongated path by a gravitational resonance with the neighboring moon Dione. That elliptical orbit means Saturn's gravitational pull isn't constant throughout each revolution. It strengthens and weakens in a rhythm, stretching and squeezing the moon's interior on every pass. Think of bending a paperclip back and forth rapidly. The metal gets hot at the bend point. The same basic principle operates inside Enceladus, except the paperclip is an entire moon, and the hand bending it belongs to a gas giant 95 times more massive than Earth. The process is called tidal heating, and it's the same mechanism that keeps Jupiter's moon Io volcanically active. Tidal heating alone might not account for all the energy Cassini measured. The South Pole was radiating roughly 15 gigawatts of thermal power, several times more than early tidal models predicted for a body this size. Something else might be contributing. Some researchers have proposed that the ocean itself plays a role, with tidal currents generating friction as water sloshes against the irregular geometry of the ice shell and the rocky core beneath. Others suggest the core is porous, riddled with cracks and channels, allowing hot water to circulate through it like a natural plumbing system, extracting heat from deep rock and carrying it upward. The exact mechanics are still debated. The consequence is not. There is a global ocean of liquid water beneath the ice of Enceladus, and it is in direct contact with a rocky seafloor. Gravity measurements confirmed it. During multiple close flybys, Cassini tracked subtle changes in the moon's gravitational pull on the spacecraft. The data revealed that the ice shell was thinner at the South Pole, possibly as thin as 5 kilometers, and that beneath it sat a body of liquid water extending across the entire moon. Not a regional pocket, not a localized melt zone, a global ocean, perhaps 26 to 31 kilometers deep, based on the moon's wobble as it orbits Saturn, wrapped around a rocky core roughly 400 kilometers in diameter. I need to be specific about why that matters, because it's easy to hear ocean under ice and move on without grasping the weight of it. Liquid water alone isn't that remarkable in the outer solar system. Europa almost certainly has a subsurface ocean. Ganymede probably does. Even Titan might have one, buried deep beneath its surface. What separates Enceladus from the rest of that list is what Cassini found dissolved in the water. During a daring flyby in October 2015, Cassini dove directly through one of the plumes, skimming just 49 kilometers above the surface. Its ion and neutral mass spectrometer sampled the spray and identified water vapor, carbon dioxide, methane, ammonia, molecular hydrogen, and complex organic molecules. Not just simple organics, large, nitrogen-bearing, oxygen-bearing organic compounds with molecular masses above 200 atomic mass units. The kind of molecular complexity that, on Earth, is overwhelmingly associated with biological processes or the chemical precursors to life. The molecular hydrogen was a particular jolt. On Earth, molecular hydrogen in ocean environments is commonly produced by a process called serpentinization, where hot water reacts with iron and magnesium-rich minerals on the sea floor. That reaction releases hydrogen and, critically, chemical energy. It's the same process that fuels hydrothermal vent ecosystems at the bottom of our own oceans. The bizarre colonies of tube worms, shrimp, and chemosynthetic bacteria that thrive in complete darkness, kilometers below the surface, powered not by sunlight, but by raw chemistry. If you could somehow shrink yourself down and visit a hydrothermal vent on the mid-Atlantic ridge, you'd find an ecosystem that runs entirely on the energy released when rock meets hot water. Finding molecular hydrogen gushing out of Enceladus meant something equivalent could be happening on that moon's ocean floor right now. Today, while you're sitting here listening to this, the silica nanoparticles told the same story from a different angle. Cassini's cosmic dust analyzer detected tiny grains of silicon dioxide in Saturn's E-ring, each only about 6 to 9 nanometers across. Particles that small, with that specific composition, can only form one way. Hot water above 90 degrees Celsius reacting with rock under specific pressure conditions. On Earth, you find nanosilica like that at hydrothermal vents and nowhere else. The same environments where some origin of life researchers believe biology may have first emerged on Earth roughly 4 billion years ago. Enceladus might be replaying Earth's origin story in real time, under the ice, in the dark. And then, in 2023, the checklist got one entry longer. A team led by Frank Postberg at the Free University of Berlin went back to Cassini's cosmic dust analyzer data, the same instrument that found the silica nanoparticles, and reanalyzed ice grains collected from the E-ring. They found phosphorus, specifically sodium phosphates dissolved in the ice, at concentrations roughly 100 times higher than in Earth's oceans. Phosphorus is one of the 6 elements essential to all known life, the backbone of DNA and RNA, the currency molecule in cellular energy transfer. Before this finding, phosphorus was the one element on the biological essentials list that hadn't been confirmed at Enceladus. Every other ingredient had shown up in the plume data. Phosphorus was the holdout. It isn't anymore. Let me be careful about what this does and doesn't prove. It does not prove that life exists on Enceladus. Nobody is claiming that. What it proves is that Enceladus possesses every known ingredient on the habitability checklist: liquid water, a sustained heat source, organic molecules of significant complexity, chemical energy in the form of hydrogen, a rocky interface where catalytic reactions can occur, salt, minerals, a pH range that, while alkaline at roughly 11 to 12, falls within the tolerance of extremophile organisms on Earth. If you sat down with a blank sheet of paper and designed a laboratory optimized for the origin of life, you'd build something that looks disturbingly like the interior of this moon. Every box is checked. The only box still open is the one that says, "Biology confirmed." That open box is what makes Enceladus terrifying in a way that differs from the usual catalogue of cosmic horrors. This isn't a world that wants to crush you with pressure or dissolve you in sulfuric acid. This is a world that might be answering the single most consequential question in science, and we can't get to it. The ocean is right there, roughly 30 to 40 kilometers below the surface on average, possibly as thin as 5 kilometers near the tiger stripes. The water is literally shooting itself into space, as if the moon is handing us free samples, labeling them, and placing them on a shelf. And we still don't have a spacecraft designed to catch them properly. Cassini's instruments were conceived in the late 1980s and built through the 1990s. The mass spectrometer that analyzed the plumes was never designed to detect biosignatures. It was built to measure atmospheric composition, identifying which gases were present and in what ratios. Finding complex organics with that instrument was like trying to read a novel through a keyhole. You can tell there's text on the pages, but you can't resolve the words. A purpose-built astrobiology mission carrying modern instruments, amino acid detectors, chirality analyzers, high-resolution mass spectrometers, could do what Cassini physically could not. It could tell us whether those organic molecules were assembled by geology or by something alive. Several mission concepts have been proposed, and none have been approved. The Enceladus Life Finder, known as ELF, was pitched to NASA in the mid-2000s as a dedicated plume sampling orbiter. It wasn't selected. The Enceladus Orbilander concept, studied by the national academies, envisioned a more ambitious approach. A spacecraft that would first orbit Enceladus and fly repeatedly through the plumes collecting samples, then land on the surface near the tiger stripes to analyze fresh plume fallout deposited on the ice. The 2023 Planetary Science Decadal Survey flagged it as a high-priority flagship mission for the coming decades. Funding and development timelines remain uncertain. The European Space Agency has discussed similar concepts at the study level. Nothing is approved. Nothing is under construction. Nothing is scheduled to launch. Meanwhile, Enceladus keeps spraying. There's a deeper problem that doesn't get discussed enough, And it's one of those details that sounds almost absurd until you think it through. Contamination. Not contamination of us by Enceladus, contamination of Enceladus by us. Every spacecraft we've ever built carries hitchhikers, bacteria, spores, organic residues from the assembly room, from the technician's skin, from the Florida air that touched the rocket fairing before launch. Most of these organisms would die instantly in the vacuum of space. Most, not all. Some bacterial spores can survive radiation exposure, extreme cold, and the vacuum of space for years, possibly decades. If a spacecraft carrying those spores crashed into Enceladus and somehow breached the ice, even in a small way, those terrestrial organisms could potentially reach the ocean. And then we'd have a nightmare scenario. We'd send a follow-up mission to look for life, find biological signatures, and have no way to know whether we were detecting native Enceladian biology or contamination from our own earlier visit. We would poison the experiment before running it. That's precisely why NASA destroyed Cassini. They flew it into Saturn rather than risk an uncontrolled impact on Enceladus or Titan decades from now, when the spacecraft's orbit eventually decayed. The agency valued the scientific integrity of a moon's ocean over a functioning multi-billion-dollar spacecraft. That decision, more than almost anything else in the mission's history, tells you how seriously scientists take what might be living down there. If you could somehow stand on the surface near one of the tiger stripes, the experience would be alien in the most literal sense. The gravity is roughly 1% of Earth's. You'd weigh about as much as a large apple. The sky would be black, no atmosphere to scatter light, and Saturn would dominate the view overhead, its rings cutting a razor line across the planet's face. The ground beneath your feet would be fresh ice, recently deposited by plume fallout, possibly only years or decades old. And from the fracture ahead of you, a curtain of ice crystals would be rising silently into the void, catching the faint reflected light from Saturn and glittering as it climbed. No sound. Enceladus has no atmosphere to carry sound waves, the most geologically active surface in the outer solar system, and you wouldn't hear a thing. Just silence, and a column of frozen ocean climbing into space. Beneath your boots, maybe 5 kilometers down at this location, is liquid salt water. Warm, liquid salt water. The temperature difference between where you're standing, minus 201 degrees Celsius, and the ocean below, possibly above zero, represents one of the steepest thermal gradients across the shortest distance anywhere in the solar system. You're standing on a frozen lid with a warm, chemically active sea directly underneath, separated by less distance than many people commute to work. The plumes themselves behave in ways we haven't fully explained. Their intensity varies from flyby to flyby. Sometimes they were vigorous, producing tall, dense columns that Cassini could practically taste. Other times they were subdued, barely visible against the blackness behind them. The variation correlates loosely with Enceladus's position in its orbit. Stronger when tidal forces pull the tiger stripes open near apoapsis. Weaker when compression squeezes them shut near periapsis. The fractures are breathing, flexing open and closed as Saturn's gravity kneads the ice on a 33-hour cycle. But some of the observed variability doesn't align neatly with tidal predictions. Pressure surges in the subsurface ocean, thermal fluctuations at the water ice boundary, structural shifts in the ice shell we can't track from a billion kilometers away. We're watching a dynamic geological process we only partially understand through the memory of instruments that were never designed to watch it. The composition might vary between individual tiger stripes too. Cassini couldn't distinguish the 4 fractures with enough spatial resolution to say for certain. A future orbiter with tighter instrument focus could map each vent individually, measuring the chemistry coming from each crack. If one vent produces more hydrogen, while another produces more methane, that tells you the ocean floor beneath each fracture is different. Different temperatures, different mineral compositions, different reaction environments, possibly different potential for biology. There's something almost cruel about the timing of all this. We identified what might be the most habitable environment beyond Earth anywhere in our solar system, and the window to study it slammed shut in September 2017, when Cassini was deliberately plunged into Saturn's atmosphere. NASA chose to destroy the spacecraft rather than risk it eventually drifting into Enceladus or Titan and contaminating their oceans with terrestrial microbes. That was over 8 years ago. No new mission to the Saturn system has launched since. The next planned visitor, NASA's Dragonfly rotorcraft, is heading to Titan, not Enceladus, and won't arrive until the mid-2030s at the earliest. One scenario that genuinely unsettles researchers is the possibility that we could eventually send a mission, fly through the plumes with the most advanced instruments humanity has ever built, analyze the organic chemistry at exquisite resolution, and still come away without a definitive answer. Biology and geology can produce similar molecular signatures through different chemical pathways. Amino acids form naturally in meteorites with no biological involvement whatsoever. Methane emerges from rock chemistry as easily as from microbial metabolism. A negative result wouldn't prove life is absent. An ambiguous result could spark decades of unresolvable debate. The only path to certainty might be to physically penetrate the ice, descend into the ocean, and look directly at whatever is down there. That means a submarine on another world. A probe capable of drilling through kilometers of frozen shell to reach a pitch-black, alkaline, high-pressure alien sea. The component technologies exist in fragments, scattered across different laboratories, agencies, and countries. The mission architecture to pull those fragments into a single functioning vehicle, the political will to fund it, the 20 or 30 years of development it would demand. That's the real distance between us and the answer. Not 1.4 billion kilometers, decades of human decision-making. If we found life there, even microbial, even a single-celled organism anchored to a mineral chimney in a dark ocean on a moon most people can't spell, the implications would cascade through every field of science simultaneously. It would mean biology is not a one-time chemical accident on one lucky planet. It would mean that wherever the right conditions converge, water and energy and chemistry and time, life follows. It would mean the probability estimates for habitable worlds across the Milky Way shift from cautious speculation to statistical near certainty. Every rocky moon with a subsurface ocean, every exoplanet in the habitable zone of a distant star would become dramatically more likely to host something living. One confirmed detection on one small moon would fundamentally redraw our understanding of where we stand in the universe. And the inverse is almost as staggering. If Enceladus has all of this, every ingredient, every condition, every energy source, and life still didn't emerge there, that tells us something profound too. It would mean the gap between chemistry and biology is wider than we thought. That the spark requires something we haven't identified yet, something rarer and stranger than a warm ocean touching rock in the dark. That's the weight Enceladus carries. 500 kilometers of ice and rock, a world you could drive across in about 5 hours, holding what might be the single biggest answer in the history of human inquiry somewhere beneath its surface. And all we can do for now is study old data from a spacecraft we destroyed 8 years ago, propose missions that haven't been funded, and watch the geysers in archived images. Right now, as you're hearing this, columns of ocean water are blasting through fractures in the south polar ice of a tiny moon circling Saturn. The water freezes into microscopic crystals, drifts into the vacuum, and joins a ring so faint it's nearly invisible against the surrounding dark. Some of that water carries the chemical fingerprints of a warm, chemically active seafloor. Some of it contains molecules complex enough to make a biochemist's hands shake. All of it is falling back into the silence, unsampled, unexamined. Enceladus isn't loud. It doesn't announce itself with crushing radiation belts, or planet-sized storms, or atmospheres made of acid. It just leaks evidence, one plume at a time, into the stillness around Saturn, practically whispering. And the terrifying part isn't what it might be telling us. It's that we might choose not to go back and listen for a very, very long time. Thanks for watching, and I'll see you in the next one.